Hello, everyone. I welcome you all after the lunch session to this third training session. And in this training session, I would like to demonstrate some of the dynamic meshing capability of OpenFOAM from the beginner level. So I am Chandan. I'm currently a postdoctoral research associate at the University of Edinburgh. And this training material I have prepared in collaboration with Joel, and you all know Joel. He has done a lot of contribution in the OpenFOAM tutorial. And I have taken some of the material of his previous training sessions on dynamic meshing, and also I have taken our tutorial repository of OpenFOAM. So these two are the main reference. So who are we? I have already told that I'm a postdoctoral research associate currently in the Vortex Interaction Laboratory in the School of Engineering, University of Edinburgh. And my broad research interest lies in the fluid structure interaction and unsteady aerodynamics. Mostly, I am interested in different bio-inspired engineering problems like development of micro-aero vehicles based on insect flight, or development of some micro drones based on passive seed propulsions. And I do not need to give a broad introduction of Joel because you all know him. He's an assistant professor in the University of Genoa, and he's also the CTO of the company Ult Dynamics. His main interest of research are also multi-physics simulation, numerical optimization, and data analytics, data visualization, etc. We are also fortunate to be part of the OpenFOAM documentation and tutorial technical committee, where we contribute a little to improve the documentation of OpenFOAM. So as I said, so in this today's training would be at very beginner level. So most of you or some of you might feel it to be very trivial, but the main motive of this training session was to touch upon and demonstrate what are the different capabilities we have in OpenFOAM and how we can incorporate these capabilities in more complex problems. So these two are the main reference of today's tutorial or this session, as I've already told. So this is the brief agenda of the tutorial session, and I will keep it very informal because it's not a formal talk. So feel free to stop me and we can discuss on maybe possible applications and how we can extend the capability and so on. So we will just go through like this. I'll first give you a brief introduction on what are these dynamic meshes, and I will go through one or the problems in sequentially in these capabilities that OpenFOAM currently has. One is mesh morphing, overset meshes, moving rigid body motion of the mesh, the complete whole meshes, then sliding meshes, and a brief intro about adaptive mesh refinement. So in this picture, you can see a demonstration of the mesh motion in case of a mesh morphing, where an airfoil is moving and based on an inner and outer radius in the domain, in the near field of the airfoil, the mesh is morphing and getting stretched and moving in the prescribed motion that is given by a predefined function that OpenFOAM already has the capability of. So this, as I told, it's a very beginner level training session, and the tutorial cases that I will present, I have tested it for the OpenCFD versions, the recent versions, and I think with slight change of the keywords, it will also work with the .org version. And please feel free to stop me, and or the online audience, please feel free to post your queries in question answer session. So there is a chat. Okay. So through this dynamic meshing strategy, it basically allows us to incorporate mesh motion in our simulation. So why do we actually need to move the mesh? To accommodate different kind of problems that we want to simulate. For example, the one problem that I showed before, to simulate the unsteady flow around a flapping airfoil. To simulate that, you want to incorporate that body motion. Either that can be a prescribed motion or that can be a fluid structure interaction induced motion of the body. So to incorporate that, we need to incorporate the mesh motion strategy, which is basically very much necessary for the arbitrary Lagrangian Eulerian framework. And if you can see that for a general transport variable phi, if we cast the Navier-Stokes incompressible Navier-Stokes equation in the ALE form, we see that in the convective term, we have a mesh velocity, which is here UG. So due to this mesh velocity, basically to incorporate this, we need a strategy of moving the mesh in different ways, and which automatically means that when the mesh is moving, or especially when the mesh is morphing, the volume of the cell or the shape of the cell is not remaining constant, which is changing with time. So of course, inherently, we need more stringent numerical conditions for this kind of moving mesh problem than in comparison to a static problem. So as I've already told, that this kind of mesh motion can be achieved through morphing the mesh, or adding or removing new cells, or utilizing sliding meshes, or using the overset meshing strategy. So overall, the bottom line is that this kind of mesh motion strategies should not be a limitation for any kind of physical problem. So they in OpenFOAM, the libraries that are developed for dynamic meshing should be utilized to any physical problem or any different solver that you want to use it with. Whether, keep in mind that all the solvers that are currently available in OpenFOAM does not implement this kind of mesh motion strategy. So that is something to remember. So this is also, I have already described that why do we need dynamic mesh? We need dynamic mesh for different things, for prescribed body motion, rigid body motion, fluid structure interaction, or mesh refinement or unrefinement. So the first example that you can see is the motion of a cylinder, which is oscillating due to a given prescribed body motion, let's say A sine omega t, with a particular amplitude A and frequency omega. And the second, and the mesh is morphing. So the first example is an example of mesh morphing. The second example, as you can see, that it's an example of a flapping airfoil, but the inner rotor is only rotating with a prescribed motion, but the outside stator part, which is not rotating. So basically there is two cell regions in the domain. So one region of the cell is sliding over the other regions, and the solutions are getting interpolated at the patch, which is an example of a sliding mesh, or the interface is called arbitrary mesh interface, where the interpolation takes place. And the third example, you can see it's an example of adaptive mesh refinement, where the mesh gets refined based on a scalar variable that is of your interest, that you want to capture with. So this is an example of rising bubbles, and here the scalar based on which the refinement is getting done is the alpha water ratio. So basically volume ratio of the liquid and the air. So some more examples to give you, including the overset mesh capability. So this capability currently is only implemented in the OpenCFD version. And so here I'm trying to demonstrate three examples of flapping airfoil, and all three cases, they are moving with a prescribed predefined motion function. And the first option, you can see the AMI, arbitrary mesh interface method. The second option I've already shown you is the mesh morphing, but the third option is what is called the overset meshing strategy, where an overset mesh moves over and background Eulerian mesh, and within the overlap region interpolation gets done. So I will describe it in a bit detail as I come. But you can say that in OpenFOAM, to simulate one particular problem, which is moving body, you can actually take resort of different type of mesh motion strategies, provided you tune the problem with considering the pros and cons of it and the numerical accuracy of the problem benchmarked with some experiments. So In OpenFOAM, in general, this is a very beginner level information that all the dynamic mesh capabilities are basically controlled or prescribed through a single directory. So if we all know that any OpenFOAM simulation has the basic structure of 0, constant, and system folder. So within the constant folder, there is a dictionary called dynamic mesh dict, which describes what kind of mesh motion we want to incorporate for the desired problem. So, and this is also very intuitive that when we want to incorporate a mesh motion, we want to also have, we have to define a particular body motion, and that body motion can be defined in different way, depending on whether the body motion is a prescribed motion or it's a fluid structure interaction motion. So sequentially, I'll show you some examples of both the prescribed motion and a fluid structure interaction problem. And this motion, it's very important that can be given either to a patch, which is a boundary of a body, or to a cell region, or it can be given to the whole domain of the mesh that I will describe as a moving mesh problem, where you basically move the whole mesh with a prescribed motion or multi-motion or fluid structure interaction induced motion. In particular to the adaptive mesh refinement, we have to define a refinement criterion that I have already told, and that should be a scalar field. And please note that that scalar field can be also customized. So towards the end of this presentation, I will just show you a community contribution towards that, where you can code a scalar field to extract from your simulation on the runtime basis and give that as a criteria to refine your mesh to capture the problem. And in the boundary condition to implement this motion type, we have to also change the boundary condition of the patch or the wall in a similar way so that it is compatible with the mesh motion. So the patch and wall can be given calculated or moving wall velocity boundary condition. Now, the thing is, it might be curiosity for someone who is starting on dynamic mesh that what are the different libraries that can support this kind of dynamic mesh motion strategies in OpenFOAM. And so the simple thing is that, and what are the different solvers that supports this currently in the current versions of OpenFOAM. So simply we can go to our solvers, or we can go to our source code, and then if we grab this particular keyword, we'll able to see that what are the different libraries that we have which supports the dynamic meshing capability. So here I have just shown one example of based on the version 21.12, and you can do that easily if OpenFOAM is installed in your computer. And we can also go back and have a closer look in these two particular folders in the source code folder of our OpenFOAM installation directory, because we are going to use this in the sequential examples that I'm going to see or I'm going to demonstrate. So I'm not showing you that, but if you have the computer, you can do this, or towards the end of the talk, I will show you what are the different folders and what are the libraries that we currently have. So this is a very important aspect that I thought I should mention, that when we are using this kind of moving mesh problems, we should also take care of the numerical setups of the solver, which are normally defined in the two dictionaries. One is FV schemes and FV solutions. Why? Because when my mesh is moving, we know that, especially for the mesh morphing, we know that our cell volume and shape of the cell is getting changed, and which also gives rise to sometime the local change of the CFL criteria for the schemes. So we have to take care of this depending on what type of mesh motion that I'm going to implement. So particularly, for example, for the adaptive mesh refinement, as the mesh changes and the cells gets refined more and more, locally the cell volume gets smaller and smaller, and our CFL number changes from refinement level to level. So this is a very important criteria to ensure the stability of your simulation. That so it's not that we can just implement the mesh motion, we have to accordingly tune the different finite volume schemes and solution mechanism that we are setting for that particular simulation. And as I said, that for the stability, to control the CFL number is very, very important for any simulation. And it's also recommended to always monitor the mesh quality. So OpenFOAM has the capability that when we run a mesh morphing simulation, at every time step, it shows you the mesh parameters, and whether at that particular time step your mesh parameters are okay, or it is going beyond the threshold limits that you have set. So accordingly, you have to take a decision whether you want to continue the simulation or stop the simulation and remesh the problem with the previous solution. So this is the problem of remeshing, which can be opted for a mesh morphing problems by monitoring the mesh quality at every time step of the simulation. And dynamic mesh problems are inherently unsteady. It's very intuitive, and it's also computationally expensive. So now I will just go one by one to these different mesh motion capabilities, and I will show you some examples and how the case setups looks like, and what are the different criteria that we need to ensure for the successful simulation. So the first capability is mesh morphing. This mesh morphing is also known as mesh diffusion and mesh smoothing techniques. And as I said, that this motion, I will show you two examples in a while, where as I said, that for the first class of the problem, we move the body and the mesh with some predefined function, right? So it's a prescribed body motion. So in this first class of problem, how do you incorporate this body motion? So that can be through some predefined function, which is already coded in the OpenFOAM libraries, or you can also do it through an input table, which is sometimes very useful when you want to incorporate some sort of very complex body motion. And these functions or the input table will be just a combination of linear time and the linear displacement and the angular displacement. So yeah, this I have already told that you have to keep monitoring the low quality meshes and the mesh quality at every time step when you are morphing the mesh. And the time step also be accordingly chosen if you are going for an uniform time step method, or it's better to go for an adaptive time step method where you are choosing a particular maximum CFL number as the criteria of the simulation. Yes, so I have told this. So the first example that I'm going to demonstrate in this class of mesh morphing is an oscillating cylinder with a prescribed motion, which is a very basic tutorial problem and easy to demonstrate different capabilities. So before that, so far, do you have any questions what I have presented? I'll be happy to answer them. Or I should continue. Should I continue? It's becoming more like a presentation than a tutorial, but I hope I'll show you some hands-on thing soon, right? So these are the different components of a dynamic mesh dict for a prescribed predefined function. So the first one should be the mesh motion library. So the mesh motion library in this case is dynamic motion solver FBMesh. So if you remember that when I showed in your source code directory, if you grab dynamic mesh, dynamic FBMesh, you see different source codes which supports dynamic mesh motion. So this is one of those mesh motion library. And within that, this lib file, lib.so file is the library file of the same, which is motion library. And the next one is very important. So within that motion library, there are many motion solvers. So you have to choose according to your problem, what type of motion solver you want to incorporate to achieve what you want to simulate, right? So in this particular case, it is chosen as displacement Laplacian. That means that we define the body motion in terms of its displacement, and the mesh morphs following a Laplacian equation. So it's the next one is the diffusivity, which is basically nothing but displacement Laplacian coefficient. So it is based on a diffusivity function how the mesh will morph. And OpenFOAM has many different diffusivity models, which I will also show you in a while. So in this particular case, I've chosen a mesh diffusion method, which is inverse distance, and that is applied to a moving boundary, which is here as a cylinder. So in the mesh picture, if you see that the patch, it is acting on a patch, and that boundary is a moving boundary, and its name is given as cylinder. And we are basically applying the inverse distance displacement Laplacian method on that. Yes, so also mesh morphing, if you find a loose definition of it, it's basically nothing but it is based in diffusing and propagating the mesh deformation all over the domain. Now I'll come in a while that even there you have control in the code where you can give inner distance and outer distance to define how much distance near the body you don't want to deform, because that can create instability for a very high displacement problems. So in OpenFOAM, as I said, there are many mesh morphing methods. So first one is the motion solver that I explained. One of them I took as displacement Laplacian, but there are many others. One is solid body, another is velocity Laplacian. So just to give an example, in the velocity Laplacian, you define the velocity of the body instead of the displacement. Now, once you choose the solver type, you have to choose the diffusivity model, right? So in the previous example, we have chosen the inverse distance diffusivity model, but there can be many, like you can see here inverse volume, and there can be many other like exponential, which you have to choose according to your problem and the accuracy of the results that you are obtaining in comparison to some reference results, right? And within that, what are the prescribed motion function? They can be oscillating displacement. That means if the body is oscillating following a periodic motion like a sin omega t, it can be angular oscillating displacement if it is pitching or rotating following an oscillating function. It can be also time varying mapped fixed value. That means if you can code a motion and you are varying it as a function of time, and you can impose that as a function. So those kind of capabilities are also possible. And this is the syntax for running a case if you don't want to really solve the problem, but want to see how the dynamic mesh behaves, and whether the mesh quality is becoming within the threshold that you have prescribed. You can just apply move dynamic mesh with no function object. Then you will be able to see how the mesh moves. So in this case particular, this is an example, as I told, that if I choose displacement Laplacian, I have to define this motion somewhere, right? So where is that dictionary? So that dictionary is within the 0 folder where you define initial and boundary condition, and there will be a file called point displacement within which you will define this function. So in this particular case, I have chosen a function called oscillating displacement, where I define amplitude and I choose whether it is in X, Y or Z direction. And then I choose a omega, that means angular velocity in radian per second. And there is a dummy value for paraview. And basically, if the patch is moving, similarly, you have to also change the boundary condition, as I said before, to moving wall velocity. Instead, if you choose velocity Laplacian, there will be a file called point motion u within the 0 folder. Sorry. And you can actually define similar predefined function there to implement the body motion. So what will be the changes in the numerics in this case? So we are basically incorporating two things. One is cell displacement in this case and the diffusivity. So in the solution setup of the solver, we have to solve for another variable, which is cell displacement. And also in the FV schemes, we have to solve a Laplacian function, which is a function of diffusivity and the cell displacement. So this is the changes that is required from the numerics point of view. So this is the example of this predefined function that I showed you just now. If you see that, you can see what kind of motion the mass is undergoing due to the prescribed motion of the cylinder. And the displacement is quite high in this case. I just kept it intentionally just to show you visually. But in this kind of high displacement mass motion, your solution transient will be very high and may not be very accurate. So those things we have to tune accordingly. Now the second example, yeah.
Sorry, I'm just a bit more interested in the details of how you will tune this situation for high displacement mesh motion, particularly if we have stronger, let's say worse situation. For example, engine combustion applications. For example, where you have to, let's say, model the piston motion all the way with the complex center, for example. So,
yes, I understand. So each of these, yeah. Okay. In the chat, there are no questions. Yeah. Okay. I see. I got it. So the question that you are asking, if I understand correctly, that as I said, that this is a very high displacement of the cylinder, which affects the quality of the mesh, right? So if the mesh stretches or compresses, that means the skewness and the non-orthogonality, all those mesh parameters are going beyond the threshold value, and at some point your solution will diverge. But there may be situations where you want this kind of high displacement, which can be prescribed or maybe FSI induced. How to simulate that? So this is your question. So yeah, so basically there are two solutions for that. One would be that, so I'll give another example for that, which takes your situation. Let's say you want to simulate a rigid body, 6 degrees of freedom rigid body motion of a falling body, right, which is unconstrained. So there is no constraint and it can rotate and displace in 6 directions and it's moving. And if you want to simulate that problem using mesh morphing, it's very challenging, right? At certain point, the mesh will be stretched and then it will fail. So if you want to use mesh morphing, the solution is remeshing. So basically you have to keep running the simulation, and as I am telling again and again, it's very important that at every time step you monitor the mesh quality. And in OpenFOAM, in the mesh morphing simulation, actually you can see the mesh quality in your log file at every time step, and it says whether the mesh is okay or not, provided the threshold values that you have given. So when you see that your mesh quality goes beyond the threshold, and you stop the simulation and remesh it with the finer remeshing and map the value from the previous solution. So there is a dictionary called map field, which can map the solution from one setup to another. And you can restart the solution with remeshing the problem and then continue till the mesh gets bad, and then you restart again.
This is not automated procedure.
Sorry?
This is not automated procedure.
Yes, it is not also robust and it has to be done manually. So that's the reason I will come to another type of mesh motion problem, which is called overset motion. This overset meshing can give you solution to that, because in case of overset, your mesh is not morphing and one mesh is just gliding over another stationary mesh, and because of interpolation, maybe the solution might not be that accurate. I'm not going to that comparison. That is something you have to benchmark with some reference, but you have no solution. So if you now imagine the same problem of a falling body, and you have an overset mesh on the body which is gliding over a background mesh, and in the interpolation region the solution getting mapped from one another. So I'll come to the different parts of the overset meshing. So that is a solution. So this I would say that there are two solutions. One is remeshing, which is not so robust. Another is overset meshes. So any other? Yeah. Okay. So can you repeat the question? What should be the selecting criteria for mesh diffusivity method? Yes, so I would show you what are the different mesh diffusivity method, and I will also show a comparison. And the criteria is basically based on your particular problem. I would say that the problem that you want to simulate, you have to try different diffusivity criteria and benchmark it with respect to the accuracy of the solution, and then you have to choose it. So there is no thumb rule for that as far as I know. Okay, so the next type of prescribed motion that I was telling, which is very useful, it can be through input table. So instead of a predefined function, you can first generate a table which can be 6 degrees of freedom motion. That means in this table you can see the first column is the time. You choose up to from this time to that time. Then the 3 components are the displacement component, and the last component is the angular displacement component. So you choose how the body moves. So you can write a script based on the kinematics you want and generate this as a DAT file. And then you can incorporate that DAT file as a tabulated 6 degrees of freedom motion, which is basically not a FSI movement. It is a prescribed motion, but you can actually tabulate the function as far as you want. Like it can be as complex as you want, right? So it is a very useful tool for a prescribed motion, but we have to keep in mind that within this, when we define, we have to choose the type as solid body motion displacement. So previously it was a different library, but now it is a different library, and the solid body motion function is the tabulated 6 degrees of freedom function, right? So so now this is an example where basically if you now notice this function, I have basically changed the table in such a way that it goes upward and then goes horizontally. And then if you simulate that, you would see something like this, right? So which is a very useful function function of OpenFOAM, where you might want to simulate a moving body problem which does not fall under the very intuitive periodic functions. Yes.
I have what would be if the inner geometry is also rotating continuously instead of just the mesh?
So the boundary is deforming, you are saying. Yeah, so that's a fluid structure interaction problem. So you cannot simulate through this. So this is just, you can do that, like let's say solids for foam, or previously FSI foam, that kind of solver you can use to. So you are mentioning the boundary of the geometry is getting deformed.
No, I'm just saying it's rotating like a sliding motion.
Yeah, you can do that. Yes, so here the third column is the angular displacement.
So that can be
Anything. Yeah. Okay. Yeah. As far as it is a rigid body problem and the boundary is not deforming, then you can give displacement components and the rotational components as a function of time. Right? Sorry, I misunderstood your question. Right. So this is an example of how can you do that, but the same precautions also applies here. As far as your mesh quality is good, you can simulate this problem, or you can go for more and more finer meshes to stabilize your simulation. And then now the question in the chat, someone asked that how do you choose the diffusivity function? Of course, as I said, I do not know any thumb rule for that. We have to try and error for the particular problem that I'm trying. So here I show you example of two different diffusivity function. One is inverse distance and another is exponential, and the coefficient of the exponent is 0.6, and you can visualize what kind of difference you see in the dynamic meshing, right? So this is something we have to try and error for the particular problem that we are trying. Right. So yeah, so here I basically list out what are the different diffusivity function that you can choose. So one, we chose inverse distance, it can be inverse volume, and this is an example of where there is two bodies. There are two bodies. So instead of one cylinder, you have, let's say, two cylinders. I will show the simulation in a while, and you can apply the same motion with the two boundaries. Instead of one cylinder boundary, you have cylinder 1 or cylinder 2, whatever name we have given, and you can see and when prescribe the motion within the 0 folder, you also give the similar. In cylinder 1 boundary, you give one kind of motion. Like, let's say in this case, in the cylinder 1 case, I've given a vertical oscillation, and the second case I've given a horizontal oscillation. And if in the commented part, you can see in the opposite direction, in the negative direction. So basically these two examples, you will see something like this. So if you have two bodies, the similar implementation applies for the boundaries. And in the first case, you see that both are vertically oscillating up and down. But the second case, one is oscillating up and the second one is horizontally oscillating, right? So this kind of problem becomes more and more difficult depending on the gap of the body, because if the motion of the body conflicts with each other, and one cell would be stretched very much, and then your solution will diverge. So next, what I'm coming for the overset mesh, which overcomes these problems.
If we have some sort of topological information in the physical domain itself, will also mesh morphing strategies be suitable for.
Can you elaborate the problem that you were mentioning? So what kind of topological change you?
Well, so for example, in our case here, I don't know, like the background mesh, for instance,
in this case, there is no background mesh. There is a single mesh, because within the boundary there are no cells, right? So there is a single mesh for mesh morphing, and the whole mesh is getting morphed, and the morphing of the mesh is throughout the domain, unless you constrict it up to a certain diameter or certain distance.
Yes. So okay, in the figure on the bottom right, so let's say the boundaries of this domain are also kind of forming or moving. So in that case, I mean, I'm thinking that this is
It will be more complicated, I would say. I don't know, like, let's say you are, for a hypothetical situation, this foil is moving in a domain and you are moving a lead over it, something like that.
So I mean, the physical domain is actually changing its topology.
It will be more and more difficult, I would say. Mesh morphing would be more difficult in that case, because in this case, your motion gets damped down towards the boundary because of the boundary condition, and you can also restrict it within a certain region of the mesh. So there is something called interpolated body motion, where you can imagine that your mesh will morph within a certain radius, and outside that there will be no mesh morphing. So that kind of motion function you can use, that you restrict your mesh motion within a certain, let's say, a circle of certain radius. So there is something called interpolated body motion you can look into. So this is another problem, and the last problem in this mesh morphing, because I'm running out of time, is the very close to my research problem, which I did in my PhD, is the flapping airfoil. So in this case, as you can see that it's not a different thing. I'm just showing another example that I applied inverse point distance for 2 airfoils up and down, and it works pretty well. So, and we have benchmarked it with respect to experiments, and we got a very good validation for this. So, and next one is the Fsi motion. So if your cylinder, you are not prescribing any motion, but you are basically applying some restraint to it. Let's say your cylinder is elastically supported on a vertical and a horizontal spring, and you can control the moment of inertia and mass of the body, and you stiffness and damping of the springs. Then what kind of motion function library we should use? So here we would use a rigid body mesh motion function within the dynamic motion solver FB mesh library, and the motion solver is rigid body motion. And for this, we need since it's a two-way coupled simulation, we need a structural solver also, which solves the oscillator equation for the structure, mx double dot plus cx dot plus kx equal to f. So that solver, there are multiple solvers available in OpenFOAM. Here I have given two different examples. One is symplectic and another is Numark. And for each of these schemes, you have different coefficients related with it. And it is a weak coupling method of FSI. That means that there is no inner loop for checking the convergence for the structural solver, and every time step your fluid and the structural equations are solved in a staggered manner. But this is just to show you that this kind of mesh morphing problems can also easily handle this kind of FSI problems. And if time permits, I will go to the case setup and show you how to set up the case. Now, quickly, I'll come to the next class of mesh motion problem, which is overset meshes. And this particular statement that I've written answers your question that this kind of overset meshes can be a combination of different component mesh. So in this example, you can see that there are two Eulerian meshes. One is component mesh 1, which is the whole domain. And then second, the component mesh 2, I use a refinement zone for getting better resolution of the flow field. And the third one is the overset mesh, including the boundary where we want to implement the body motion. So basically the first two meshes remain static, they're Eulerian, and the overset mesh moves within them. And basically what happens is that within the overlap region of these different meshes, interpolation takes place from one to other. And there are three kind of cells you can imagine in this kind of setting of dynamic meshing. One is hole. Hole means that the cell where there is no cells within the main overset mesh, but there is only background mesh. So there is no computation takes place. They are called holes. And there is an interpolated zone. So I will probably show you visually, but just to show you tell you the properties that this kind of overset patches can intersect each another, even they can handle collisions and they can go over each another, and there are no problems, you can run the simulation. So this is the thing that I was telling, that basically first I will show this. So basically there are three different kind of cell zones that you can expect in this kind of problem. One is hole, as I said, that where there is no cell in the overset mesh, but there are only cells in the background meshes, and there are no computation happens. Then there are interpolation fringes, which is defined by the user. So basically this is the patch where they connect each other. One overset mesh connects with the refinement zone, and then refinement zone connects with the background mesh. There the interpolation takes place, and the interesting and very important thing is that the size of the cell in this interpolated fringe should be similar to reduce the interpolation errors. Otherwise, the errors will be very high. And then in the other colored area, where you can see the green colored, they are all computed regions. So the interpolation only happens in this interpolated fringe, and the interpolated cells can be classified as two types. One is acceptors or donors, right? So one data goes from one mesh to another depending on which data is getting interpolated on the other. Depending on that, they can be called acceptor or donors. Now, to achieve this, we have to first do some pre-processing of the mesh before running the solver. So what is the main pre-processing? We have to first generate this different component of the meshes. That is one thing, but we have to define what are those overset patches where interpolation takes place. So that is defined by the users. And then we have to assign different zone IDs, which are nothing but the markers for those cell zones, to these different meshes, so that the overset solver can understand which one is the whole region, which one is the interpolated fringe, and which one is the computed region. And which is basically the compute stencils. They would determine the compute stencils based on these zone IDs that we define in the solver. And this, the most important fact here is what kind of interpolation technique that we are using, right? So in OpenFOAM, we have multiple interpolation methods within these overset zones. So these three are the most popular. One is cell volume weight, which is first order accurate, but it is fast, but it has problems with detecting the cells in the hole. And second is inverse distance, which is second order accurate bounded, but it's expensive. And the third one is least square, which is very expensive, but the accuracy is quite good. And we can also debug what are the cells that are basically computed and demarcated as these holes, interpolated, and the computed region by this toggle key of debug switch overset 1 in the control dict file. Now, the thing that I stopped telling you that there are cons, like you cannot really consider overset to solve all your problems, because accuracy wise mesh morphing is more accurate in my experience than overset methods. And because overset mesh can add numerical diffusion to the solution, and interpolation is always having some error. It's like how much you can minimize the errors due to interpolation by matching the size of the cells in the interpolation regimes. And in the overset meshes, cell size close to the overset patches should be similar. That's what I have already mentioned. So now by that, the same problem, if we which we dealt with the mesh morphing, it comes like that. So basically in this case, in the prescribed motion, you prescribe the similar motion functions on a body and the overset mesh on the cell zone, which moves in an Eulerian grid. And also you can simulate the FSI problem very easily, right? There is no mesh deformation. So ideally there should not be any problem till your accuracy is good. So there is a question, a comment. Okay. So I hope that do you have any questions so far in between the mesh morphing and overset methods?
Yes, I have a question. Here, for example, in the left right for you mesh motion, you have two meshes.
Yes.
One with tetra meshes and extra in the background.
Yeah.
How do you relate them in a case file?
Yeah, so this particular case in the right side of my example, for the flapping airfoil, the meshes are generated in Fluent. So it's very easy to generate unstructured meshes. So the beauty of overset meshes is that any of these component meshes can be structured, unstructured, anything till it meets your requirement, right? So these two meshes are generated in Fluent, and I will share the link. So this tutorial and the figure is taken from the training file freely available by Joel in his website Wolf Dynamics, so you can download it. So this is a Fluent mesh file which you can import in OpenFOAM by Fluent mesh to foam, right? And the case files should be separate, so which I probably did not mention here explicitly, that I would plan to show you, but if time permits, that for overset cases, your each component mesh would have a case file. Zero constant system. So you first import the mesh there, and then you merge with the background mesh with the function called merge mesh. and then you have a mesh marched together, right? And the left hand side, this cylinder case is generated in block mesh, so it's a very easy structured mesh. And this is a very interesting capability which is developed in very recently 2106 version, where you can also move the refinement zone, which is very useful for the kind of problem at least I am dealing with, where basically if your body is moving over a large domain, you cannot really use a static refinement zone, right? I mean, it will be very expensive computationally. So the robust way would be if you create a refinement zone, which is also an overset mesh, and stick it with the center of gravity of the main body. So this capability is called driven linear motion. And so here, the example that I'm showing you is a projectile motion, which is a prescribed motion to the body. But in the refinement zone, I have given this library within the FB motion solvers. I've given driven linear motion, and I mentioned the C of G, which is center of gravity 1, which is the same of the body that I have prescribed. So what it does is it goes, reads the center of gravity at per every time step of the body and translates the refinement zone accordingly in the X and Y direction. So it doesn't rotate, but it is not a 6 degree of freedom motion also. It just translates accordingly so that you get the same resolution of the flow everywhere in the domain, right? But it is not very well developed. There are some issues, bugs reported, and people are improving on it. But this works for this kind of problem if you want to move a body for long domain or very large domain. Yeah.
For me, it was not clear the advantage of using that, because you know the of the cylinder. So if you know where it's moving, why don't move the refinement with the same?
That's what it is doing.
Yeah. But you told you are computing the center of gravity of the cylinder in order to.
Yeah, in case of FSI case. Sorry. So in case of prescribed motion, it is just reading, which is getting written in this keyword C of G every time. And in case of FSI, if let's say it's a free falling body, you don't know how it will move. So you have to compute through the, yeah, right. So, but probably I'll discuss with you later. So this particular driven linear motion actually doesn't work when there is two cell zones stitched by a boundary, which I'm still struggling with. Maybe we can discuss later. So yeah, so this is the third class of problem, and I have 10 minutes. So 5 minutes each. I will tell you about two capabilities. One is the moving mesh cases, where you basically move the whole domain and mesh for the problems like sloshing, right? Where basically it's kind of a non-inertial frame of reference and your whole domain and mesh is moving with different acceleration. So in this case, we use the motion solver called solid body. And within that, beautifully, you can incorporate multiple motion, and which is the function is called multimotion. So if you can see here, I have defined two different motion. One is oscillation, another is rotation with the same body, because I'm moving the whole body of the mesh. So I don't want to define any patch or boundary. It is applied on the whole mesh in a rigid body fashion. So no mesh within the domain is deforming, but they are moving with that motion. So like in the first and second case, I basically have defined your oscillating linear motion and rotating motion, but you can actually give these all different type of motion and test it. SDA is something used in the sieve hydrodynamics, which is a 6 degree of freedom motion again. So this is the tutorial file already available within OpenFOAM OpenFOAM versions. You can test it with, where you can see this kind of body, cylindrical body is translating and rotating, and the whole mesh is rotating, and the color contour level that you see is the alpha water. That means it's the volume fractions of air and water, how it is sloshing within this moving body. that you can simulate beautifully by moving the whole mesh. Yeah, this is the penultimate, not the last one. So this is the sliding mesh, and I won't go into detail, but I will just show you what you can do, which I have already shown you. This is a bit complicated in my experience to really do it, because the meshing takes a lot of effort, and there are two approaches to do it. One is that this particular approach of arbitrary mesh interface, it actually has to have a axial symmetry, right? Because one mesh has to slide over another mesh, so only there will be two component of mesh. So one approach is that if when you mesh it, you define the interfaces, that means the outer patch of the inner mesh to be AMI, arbitrary mesh interface, and the inner patch of the outer body also as AMI. AMI1, AMI2, and then you apply this condition, which is called cyclic AMI condition, and one has to be master mesh, another has to be slave. So basically in this case also you have to merge a rotor case within the stator, and here the rotor part is the master and the stator part is the slave, or you can define it in the either way. And based on that, you can actually use this AMI method. In here, we have used face area weight method. There are many others available in OpenFOAM if you can check. And also another important function here is transform, where I have used here no ordering, but it can be used as translational or rotational based on other input parameter, where the same thing which we try to achieve by mesh morphing, that within a certain radius only mesh will deform. Here within a certain radius the mesh will rotate in a rigid body fashion, which you can easily implement for a pitching airfoil or any rotating body with much less computational intensive thing. I mean, it is much faster in that sense and more accurate maybe. So the last one is adaptive mesh refinement, and I will just show you these settings because I have 2 minutes, and where I have already told you that based on a particular scalar variable, you can refine or unrefine your mesh, and these are the different control parameters, that what is your interest of variable. So in the previous example, I showed you the alpha water volume fraction of water and air is the interest. And you can also define what is the maximum number of cells beyond which you stop refining and so on, and there are many examples already available in the OpenFOAM tutorial branch. And this is one example where it's a dam break tutorial with an obstacle where the surface of the water and air is the alpha water ratio, which is the control parameter. And you can see that the cells are getting refined as the surface interface is moving, and this is simulated by volume of fluid method, the interFOAM solver. So it's very useful for different, particularly multi-phase problems. And this is it's a very recent development from a community person. I forgot the name. Sorry for that. Here is the GitHub link, where he shows and demonstrates that you can code a particular scalar variable. So here you can see that velocity, maximum of the velocity gradient is the scalar that you are looking in every runtime, and then that based on that maximum velocity gradient, you are refining your value. And I will show you the video that he posted. It's a very interesting development that you don't have to have a particular scalar value already predefined. You can on runtime look up and define a new scalar value, and based on that you can refine your meshes. So before I do that, I want to share that and stop this. 1 minute. Just give me 1 minute. It has been lost. Yeah. So this is the video, and his name is Nicholas. I'm sorry for forgetting your name, but I wanted to mention this development, which is very interesting to me, that in the same velocity gradient, every run time step you can calculate, and then you can refine and capture a von Karman wake, let's say, past a cylinder. So this kind of coding capability is also currently part of the recent versions of the OpenFOAM, which you can use, and the whole repository is available in his GitHub repository, which the link is given in the slide, so you can see how to code that. And I will also upload these case files in my GitHub repository, and the same are also available in the Wolf Dynamics website, in the Joel's website. So feel free to test all the capabilities. And there are some questions in the chat. Okay. How the inner or outer distance is measured? I mean to ask whether it is a rectangular or radial, how far should be outer distance from the main boundary. Again, this is beyond, this is beyond any thumb rule. It has to be decided from one problem to problem basis, and since it's a radial distance, it should obviously a circular area of cells. It cannot be rectangular. Yeah, so if you have any other questions, I'm happy to answer. And I think I prepared up to this, and thank you for your attention. You can also email me or message me or post in the question answer session if you have any particular question. I'll try to answer. Sure.
Yeah, just a quick question on the big mesh for the entire domain.
Yeah.
What's the difference between doing that and just superimposing like a velocity field on top of the domain, or are they numerically the same thing?
I would say that there is a difference in the frame of reference. So one is inertial, another is non-inertial frame of reference, but it's a two different approaches. Maybe the physics would be captured same.
But is there any advantage to like simulating the motion of the entire domain?
Yes, because let's say your body is flexible. I'm just thinking aloud. Correct me if I'm wrong. If your body is flexible and you want to simulate the sloshing dynamics, the FSI sloshing dynamics within the body, I think by imposing velocity it would be difficult. But if you use a coupled solver and use this whole move mesh approach, it might be easier. Yes.
Very nice presentation.
Thank you.
And it was not fully clear why we are using, or how we are using that refinement mesh source, because the problem is being solved in the background mesh.
Given that the cell size of the background mesh is equivalent to the cell size at the interpolate. So you basically, if you want to, let's say, I want to simulate the dynamics of a falling body, which can go horizontally anywhere, right? So if I want to capture, let's say 20 reference length scale, I have to use a refined background mesh block. But instead, if I use a refinement zone big enough that I'm only worried or only concerned about the physics inside that refinement zone, given that the boundaries are far enough, and I do not consider the outside solution, I consider it to be wrong or it to be not so accurate, but I only consider the inside refinement region, I think that makes sense, right? That will.
Then the problem is solved on the refined mesh.
Yes, correctly.
And then the refined mesh gets the boundary data from the background mesh.
Yes.
At the boundary of the
yes, and outside the refinement zone, the accuracy of the solution is not so good, and I don't.
Maybe you don't have relevant gradients.
Yeah,
there.
exactly.
Level of mesh refinement
Yes.
you are using is okay for that region.
Yes.
But not for the region of interest.
Yeah. I can also use a gradient. So I can go coarser towards the boundary within the refinement zone to make that. Yeah. Thank you. Okay, I think already 5 minutes passed. If you do not have any other question, I should close the session. Thank you.